Okay, so I need to recall a couple things, and then we'll have a motivating question. So, the thing we need to recall is projecting stuff, right? Which we did last time. So, I want to start with a vector b, and I want to think about projecting this onto a what? What were we projecting onto?
Another vector.
Yeah, so first we did projecting onto another vector, then we improved that to a more general projection, right?
Projecting onto a subspace?
Yeah, so I was projecting onto a subspace, right? So I had a map that took B, and that map was called P. This produces a vector B parallel, and B parallel is in the span of some set of A's. You guys with me on that?
Yeah.
Yeah.
What was important about the A's in order for this to work?
They're linearly independent.
Good. I wanted to make sure that these are linearly independent. If they're not, I'll drop stuff until they are, right? And now I need a formulation for my matrix P. So B parallel, right, was A done to X hat. And what was the formula for X hat?
AB transpose A, both of those things inverse.
Yep, so A transpose A is inverse.
A
transpose done to my vector B, right? So this whole thing is my projection matrix, right?
Yeah.
And I'm going to shorten that today to talk about this guy, which is my X hat. You guys with me on that? Okay, so my motivating problem, the thing I'm going to try to do, is I'm going to pretend I've got a cloud of data, right? Some data. And I would like to be able to fit a line through this data. Human beings are bizarrely good at drawing lines of best fit with no information. Like, really, honestly, it's a very cool thing about people. If you, like, look at some data, you can be like, okay, the line that best explains that data, tell me when my fingers get to the right spots.
There we go.
Yeah, notice you all said that at basically the same time, right? This is actually a really cool thing. Like, human beings are, for whatever reason, super good at eyeballing that line of best fit. So, when you feed data into Excel, right, you can get this line of best fit out of Excel. The question today is, how the hell does Excel do that? And the answer is surprisingly casual once you've got the machinery that we've built up. So this is super fun. So I'm going to motivate this with the absolute dumbest example I could, which is I'm going to put a line through 2 points using linear algebra, which is going to seem like massive overkill, and then we'll generalize that to this case. You guys good with that? Okay, so I need 2 points. I'm going to start with some points that are relatively easy to calculate. So I'm going to pick the point 1, 1, and the point 3, 2. So these are going to be my 2 points that I'm going to just start with, right? Now I want a line that goes through those 2 points, yeah? Okay. Here's the kind of linear algebra magic. You could do regular algebra to this, right? You all could be like, calculate this slope, frickin' back that out to an intercept somehow, or use point slope form or whatever, right? So I want to do this in the weirdest way I can. The weirdest way I can is I'm going to think about this function, right, this line. I'm going to think about that as a function. So I'm going to think about that as y is mx plus b. You guys all with that? And then just to confuse the crap out of you, are you writing this down? Okay, you're going to get your eraser out because I'm going to switch that order. So I'm going to call that b plus mx. I know. You guys all good with that? Honestly, just to fuck with you. Because I'm going to try to generalize to kind of higher use cases in a bit. And so I'm starting my line in increasing order of powers, because I'm going to use this same trick to fit a best cubic. I'm going to use this exact same thought to fit a best 5th degree polynomial, and I don't want to deal with the order mattering later. So I'm just going to start with x to the zeros, and then we'll go to x to the firsts. You guys good with that? So let me write down 2 equations to solve for m and b. This is not the algebra way, but it's equivalent. So I'm going to use my point 1, 1, right? And I'm going to say that's a y of 1 I'm going to completely reverse the order. I know, you already wrote it down the other way. Write it down this way again. So I've got 1 on the other side, right? And the point 1, 1 means that when I put 1 in for x, I get 1 out for y, right? You guys see that? So that means that if I do b plus m times 1, I get 1. Is that on board? How about the other point? Yeah, I'm going to do b plus m times 3, the x value, is going to equal 2. Is with me? This is not how you would algebra this, right? But you could, right? We could, like, take this equation and subtract it from that one and then divide, and we'd get the difference in the y's divided by the difference of the x's, and we'd arrive at the formula for slope. Math is a bunch of weird interconnected circles, right? Like, you can reason these things out in a lot of ways. So, what I'm going to do is I'm going to rewrite this as a system of linear equations. You guys see that? So, what are the 2 unknowns? This is the part of linear regression that trips everybody up.
The slope and the intercept?
Yeah, the slope and the intercept, right? The pieces of the line are my unknowns, right? So I'm going to rewrite this as a matrix times a vector bm. Don't worry, I'm not changing it, I'm just moving it. And that's going to give me a vector 1, 2. You guys with me on that? Okay, can you tell me about the columns of this matrix here?
Well, the first column would be 1, 1.
Good.
And the second one would be 1, 3.
First column's 1, 1, and the second column's 1, 3. That is me saying this column is x to the 0, and this column is x to the first. You guys see that? Okay, can I solve this? Yeah, absolutely. I can invert this matrix, multiply it by that side, right? And I can actually come up with a solution. You guys see that? I'm going to get that Bm is this thing's 1, 1, 1, 3's inverse, done to the vector 1, 2. Cool, check, done. You guys with me on that? Out of this, you will arrive at B and M. You can use B and M to say what your equation for your line is. You guys believe that? Okay. This is the case where what happened that was a little bit special here. So what's going to break when I try to generalize this case to this case? When I go from 2 points to more points.
Oh, it won't be a square matrix anymore. You're going to have a lot more rows than your columns and the other
You guys see that?
Yeah.
So if I put more points in, it won't be square, and I won't be able to invert it. You guys see that? So I'll lose the ability to hit this matrix against that vector and get an answer. So I'll have to do something weirder, right? So what I'm going to need to do is kind of push whatever vector I have over here onto one where I can kind of invert. You see that thought process?
Project.
I'm going to need to project it, and I'm going to need to project it onto what? So where can I invert? If I go look at the 4 subspaces, right? Which one do I know is a, like, where is a 1-to-1 part of it?
A transpose A. No.
I was gonna say.
Good, yeah, I know I can invert the matrix A transpose A. You guys see that? So what I'm going to do, right, subspace-wise, I've got my matrix A, right? And I've got my kind of subspace decomposition, right? So I've got this sort of a picture on the left-hand side, and a similar picture but tipped differently on the right, right? So I've got my one space and my space that's possibly a different size.
You always gotta emphasize that.
Right? Yeah, and I always emphasize that that one might be a different size, right? So, what are these 2 spaces that are the same size? Yeah, this one on the left is the row space of A, this one on the right is the column space of A. And my concern, right, I know that I can reverse from the column space of A back to the row space. You guys remember, where did we figure that out?
When we realized that one's a row of
It's when we got the perpendicular decomposition. Right, so when we got the perpendicular decomposition, we had a little theorem that says that the matrix A is 1-to-1 between the row space and the column space. You guys recognize that? That was me setting up being able to invert.
Right.
So I can't invert a general vector, right? So a general vector over here is going to look like this. It's not in the range, so I can't find anything that maps to it,
Yeah.
right? So what I'm going to do is I'm going to force it to be in the range, right?
Yeah.
So I'm going to take that vector, I'm going to go, nah, I don't want to deal with this vector B. I want to deal with a vector B that's in here. That's going to be a vector B parallel. If only I had a way to get a hold of that friggin' thing, right? And then I'm going to say, I need something that goes to be parallel. You guys see that? Because I'm not going to care, the B in this case, right, is the Y values. I don't give a shit about the Y values. I want to know about the line. So I'm not going to be after a B parallel. I'm actually going to be after something that maps to B parallel. So what maps to B parallel? You see that?
X.
X hat's what I'm after. You guys with me?
Yeah.
So I just need to formulate a way to get my A's, and then I can shove them into a matrix, and check, done, Bob's your uncle, you've got linear regression. Right? So, I need a way to take data and turn it into a thing like this, so that I can do that projection. That's cool with that? So let's try an example where they're not on the same line, and then we'll see if we can formulate where that stuff would be. So I have here 3 points that we dealt with last time, and those 3 points are 0, 6, 1, 0, and 2, 0. So my goal, right, is to fit a line through these things. You guys good with this?
Yeah.
So the first thing I'm going to do is I'm going to write my equations. So my equations are going to involve B, M, X, and Y, right? The X and Y are going to be things I know, right? So I'm going to say, all right, let's just suppose our line is Y equals MX plus B. And then before you write that down, I'm going to erase it. And I'm going to put BMX plus BMX equals Y. Right, just so I can linear algebra this. And I'm going to write down each of these 3 points giving me an equation, right? So my first equation is going to be what? B plus M times 0 equals 6. And my next equation is going to be B plus M times 1
Equals 0.
equals 0. And my next equation is going to be b plus m times 2 equals 0. How do I know these points aren't on a line already?
There was 2 intercepts.
Good. I have two x values that output a y value of 0, right? This line has 2 x-intercepts. It would be horizontal, right? But that one means it can't be horizontal because it has a y-intercept of not 0. You guys see this? Okay, so we're going to take this, we're going to formulate this as a matrix, right? You guys see that? So if I formulate it as a matrix, how big is it going to be?
2 by 3 or 3 by 2?
3 by 2.
3 by 3. 3 by augmented.
3 by 2.
Okay, I'm gonna avoid augmenting.
So then.
So I'm gonna set this equal
3
to.
by 2.
So I'm gonna set it equal, and I know that on the equal side, right, I'm gonna have a 3 by 1 vector.
Yeah. 6, 0, 0. And that
My
one's
unknowns are b and m, right, which is a
2 by 1.
2 by 1. And so in order to multiply something by a 2 by 1 to get a 3 by 1, it's going to have to be 3 by 2. You can reason through that a bunch of ways. Another way you could do it is you could look at this and be like, yo, dude, you have 3 equations in 2 unknowns. Right? So this isn't in general going to work, right? You guys see that? I know this one's not going to work already because it's not on a line. Right? These 3 points just aren't on a line. So I've got 6, 0, 0 over here. You guys with me? On the left-hand side, what do I have?
0, 1, 2 somewhere. Like on the one of the columns is 0, 1, 2, right? So you got 1, 0, 1, 1.
1, 0,
Oh.
1, 1, 1, 2.
Because you're multiplying, because that's its coefficient.
So I'm asking, what's the coefficient on b in each equation?
Oh!
Coefficient on b in each equation is 1.
Yeah.
What's the coefficient on m in each equation?
Okay.
Well, there's 0, 1, and 2. Those are my, again, I'm going to keep emphasizing this because I want to be able to scale up a little bit. I'm going to emphasize that these are my x's to the 0 power, and these are my x's to the first power. If I was doing a parabolic regression, right, I would have a third column that would be my x's squared,
Oh, cool.
and I would have a third item in here. And that one I would expect to be able to do, right? Because it takes 3 points to determine a parabola, and I would have 3 points. You guys with me? Okay, so what's my next step? Yeah, I should start thinking about trying to invert, right? Now, the kick is this one's not going to work.
No, yeah.
You can't invert this thing. So what do I need to project onto?
Parallel.
Yeah, I need to project to be parallel, which is in the column space of A. You guys see that? I can do that as long as the columns of A are linearly independent, right? That's where this thing came from. This capital A matrix was just these A's within the columns. Okay, see that? So I just need to know that I have a linearly independent collection of vectors that make up my column space. So are these two vectors linearly independent?
Yes.
Yeah, absolutely. So I just need to project. So the way I'm going to project is I'm going to use the formula to project. Now, I don't care about B parallel, but we'll calculate it anyways, because it's going to be right there. In fact, this was an example you guys did the other day. Do you have the numbers handy for this? I have them written down somewhere if you know.
The numbers handy for that?
Yeah, so the other day we projected, right? One of the examples I did was we projected onto the span of these two vectors.
Oh,
that
yeah,
one.
yeah, yeah. I have it in my calculator.
Right, so there's a calculation you can do.
Mhm.
Do you have it, Sandy said?
Yeah, do you want... So, I have ATA inverse. Is that what you want? Or do you...
Okay. Yeah.
So the things I'm going to be interested in are, what's the vector b that we're projecting? We're projecting 6, 0, 0, right? So we've kind of reduced our linear regression problem
Okay,
to
yeah.
project b,
This is exactly what it is.
6, 0, 0, onto the column space of our matrix over there. 1, 1, 1, 0, 1, 2, right?
Yeah.
Yeah.
The column space of this matrix is exactly the same thing as the span of the two vectors 1, 1, 1 and 0, 1, 2.
I remember what the projection matrix was. I have it.
Good. So I don't need the projection matrix. The two things I'm going to be after for linear regression are going to be B, well, three things. What's B parallel stage?
B parallel is a x.
Yep.
Oh, I see. B parallel is 5, 2, negative 1.
Okay. 5, 2, negative 1. What's x hat?
X
Well-
hat.
5, negative 3.
5, negative 3. Guess with me? Okay. What's B perpendicular? Just because I think you have it. We have B perpendicular kicking around somewhere?
No, I was just like, it's
I thought that was the third thing.
1, negative 2, 1.
1, negative 2, 1. Okay, so just to confirm, if I add these two together, I get B.
Yeah.
I should confirm that B parallel is in the column space, so it looks like 5 times the first vector. Yeah, I'm just thinking about this as, okay, so 5 times the first vector is 5, 5, 5, right?
Oh,
And then I need to be subtracting some to get to 2.
yeah, which is
So I'm going to need 3 times the second vector, so 0, 3, 6.
yeah,
Does that work?
yeah.
5, 2, negative 1. Cool. So this is indeed in the column space. I'm just checking that I have everything working, right? Normally I would just like assume that the calculator gave me the right answer, but since we did this the other day, I'm just going to double check this. You guys with me? So this vector is in the column space, which means that in the column space, right, we can pull back to the row space because the matrix is 1 to 1 there. So this is the thing that goes to that. You guys see that? This guy gives me that under the matrix A. You guys on board with that? So if I take my matrix
Oh, so that's yeah.
1, 1, 1 and 0, 1, 2, and I multiply it by 5, negative 3, I get out this vector, 5, 2, negative 1. Okay. So if I do A to x hat, I get B parallel. Guess with me?
Yeah.
Okay. X hat is the, well, B parallel is the closest you can get to B in the range of this matrix. You see that? So it's the closest I can get to being on a line. Guys with me? So really carefully, let's plot our points that we started with. So the points that we started with were 0, 6, right?
Yeah.
So 0 over 1, 2, 3, 4, 5, 6. So dot there. 1 over 0 up, and 2 over 0 up. You guys with me? This is the cloud of data I started with. It's 3 points. Yeah, okay. I'm fitting a line through 3 points. This is not, like, stupid exciting, right?
I'm excited as fuck.
But we could do this same exact procedure with much bigger clouds of data, right?
Like, this is
It would be a calculator problem rather than a by hand problem, but it's easy, right? Like, getting the computer to do this is stupid easy. So, what's my line? Well, my best fit, right, is, and I have to remember which order I put the x's in, right? So the x of 0 best fits to y of 5. Right, so 0, 5. You guys see the difference between purple and black up there? Okay.
I don't know if your camera can.
Yeah. So this is my 0, 5. That's 0 here, 5 here. Remember, this is the x to the first column that I'm getting these out of. So 1 best fits to 2. And 2 best fits to -1. You guys see that?
Yeah.
If I had a straight edge.
Hey!
Ah!
Joe!
Ah!
Joe!
God, that was going to be so good. I just botched my straight edge.
Sure.
Just draw that middle point bigger.
Yeah.
Yeah, that's what you gotta do. As a math professor.
Yeah, just make the points bigger
Yeah.
until they fit.
Yeah.
You guys with me?
Yeah.
Does that look like the line you would have had in your head?
Yeah.
I mean, it's pretty darn close, right?
That's so cool. That is actually really
Okay, so really cool question. Just to wrap this in a really fun bow. Why do they call it why do they call it least squares regression?
cool. Oh, that's R in statistics.
How far off are you here? Who knows, right?
Yeah.
Okay, so forget how far off are you in this picture. Ah, I erased the I erased the 4 subspaces picture and I needed it. So remember, over here, right? We're talking about our matrix A, right?
Oh, we're off by the.
And we've got our subspace. So
Are we off by the vector that was in the null space? Be perpendicular?
close, yeah. So here, right, is my vector B.
Yes.
It's not in the column space, so I can't solve that. So what I did was I projected it to get a vector here, B parallel,
Are we off by the
right, where I could solve it.
between the
And I'm off by the difference between B and B parallel, which Sage just said is the perpendicular. You guys see that? That's this vector. Okay. How long is the perpendicular vector?
the magnitude. Oh wait. Ah.
You guys see that?
Yeah.
If you want to figure out how long a vector is, right? What do?
You take the magnitude.
Yeah, you take the magnitude, which uses the Pythagorean theorem.
Yeah.
So you square the components.
Oh wow.
Adam.
It all circles
And we just
back.
made the squared error as small as possible. That's why we call it least
Holy
squares.
shit. That's so cool.
And it's the difference between the B parallel and B perpendicular, right?
wow.
So if I look at those, right? What's this 1 here? That 1 is 6 minus 5.
Yes, it is.
Right? Which is this vertical distance.
Yes.
You guys see that? That's the x component of B perpendicular. Right? That's 6 minus 5 equals 1. This one?
Like your brain is going crazy, dude. Come on.
Oh, it's 2.
It's
Yeah.
2. It's negative
that
2 in
one
B
is
perpendicular,
1.
but I'm going to square it when I figure out how long this vector is anyways, right? So that vertical displacement is 2. How about this one?
1.
That was a vertical displacement of 1.
Oh.
So the closest I can get, right, is the square root of the sum of squares of these vertical distances. That's why it's called least squares. Because you're minimizing the square distances that you are off in the y's.
That's so cool. Man, I wish Arsh was here.
You
He'd
guys see
love
that?
this. Oh my gosh.
Okay, so what do you do to get least squares regression? Like, let's just back up. So I need to project.
You need to find
What do I need to project onto? Because that's clutch.
onto the column space.
Onto the column space of what?
A.
Yeah.
Of
What?
It's the span.
span
Like,
of
A wasn't anywhere to begin with, right?
Yeah.
I made up my matrix
On
A.
the coefficients
Yeah.
of the equations generated by those
Yeah.
small.
Yeah. Like
Good.
you line
So-
them up.
You need to write your equations, right? With your coefficients. Alternatively, if you're doing this in the future, the first column is all ones.
Oh,
The second column is all
X's.
x's, and the thing you're projecting
Wise.
is all the y's. Just keep the x's and the y's in the same order, and then you can use this as your matrix, right?
Yeah.
You see that? There's some tricks in the textbook to make this faster, like computationally faster, for the computer. It involves recentering, like making your average distance 0. It makes your matrix just a little bit nicer, but you can do it with these. It'll just take a little longer if you're doing 10,000 data points. You guys cool with this? Yeah.
So with A and B parallel, it's like makes sense. Like, is there any significance for x hat? Like, is there any cool significance? I guess.
Yeah, I mean, the cool significance is that that's my line.
Okay,
I guess I
that's what
didn't
thought.
really
Okay.
say this super explicitly. This purple line, that line of best fit, is 5 minus 3 x equals y.
Okay, that's what I was thinking of when.
You can see that? So if I was going to do this with a quadratic, right, the coefficients would be the x hat, right?
Yeah.
I would have 3 of them. And the coefficients would be the x to the 0 coefficient, the x coefficient, and the x squared coefficient. And then the 3 columns in my matrix A
Yeah.
would be the x to the 0s, x to the 1s, and x to the 2s.
Okay.
Sick.
You guys good with this? Okay. Any other questions on these? Okay. Oh, sometimes the vector be perpendicular is called E for error.
Okay, yeah.
I should just
okay.
add
That's how it is in the homework.
Yeah.
Okay, cool.